and I'm happy to give this talk once again. I've given it many times, various places. And it is all about the rather provocative suggestion that we have been making over the years that there are pieces of continent occurring in the earth in places where they shouldn't be, in places where you don't expect them to be, and that is the subject of the talk. So it's hidden continents. And really the talk can be summarized in the title of this paper that was published about a year ago in Nature Communications. So it's about Archean zircons in young oceanic hotspot-related volcanoes that establish what must be the presence of a piece of continent under the volcano at Mauritius. So the work represents a collaboration between three people. Me, I'm a rock guy, so I know about rocks and minerals and something about geochemistry and petrology. The second guy, Michael Wiedenbeck, he's the laboratory guy. So he is the analyst who produced these fantastic ages of the zircons that you'll see about today. And the third guy, most of you know this guy, Trond Torsvik, Norwegian guy. He's the guy who reconstructs continents and moves them back. He's a paleo-mag guy, and he's now into global geodynamics kind of things. And so it's a very interesting collaboration of three people whose expertise is quite different. So the collaboration was a very fruitful one. And so the talk today is going to be, for better or worse, mostly geology, a little bit of geophysics, and a little bit of geochemistry. The opening picture sort of encapsulates two important things about Mauritius. One is that it's a beach resort, holiday, beach paradise place. You all know about that. And the second is that there's big mountains there that are volcanic in origin, but one good question is, why is the elevation so high? I'll talk about that a little bit later on. You know, this research paper appeared in a pretty high-profile journal called Nature Communications, and it was, the embargo was lifted, as I remember, on the 31st of January last year at 4 p.m. And at 4:01 p.m., my phone started ringing, my email, my desk phone, my cell phone. Media went crazy with this. And I still don't understand why, really. I have some ideas, but, you know, this is just a small assortment of people who I've given interviews to, and so my name has appeared everywhere. I got a phone call from the science reporter at the New York Times. How often does that happen? So I talked to this guy for an hour, and then he called me back and wanted more stuff. It was really, really quite interesting, but I assure you, I did not ask for this. This is not the kind of thing I try to seek doing. I am not Lee Berger. He does this for a living. And this got far more media recognition than anything he's done, and I'll show you. And I didn't really ask for this, so it was kind of fun to talk to, you know, all of these. Look, Cosmopolitan magazine. My name appears in Cosmo. Who would have expected that kind of thing to happen? So it was very interesting and kind of fun, but I assure you it was really exhausting. I must have done about 40 interviews in a period of about 2 weeks, and it was on live TV and live radio. I did a live radio interview in Bogota, Colombia. Yes?
Did you give any local interviews?
Yeah, I didn't put those in there, but...
ANN 47.
I don't think ANN... You remember who it was.
I saw you on ETV.
ETV, okay.
Yeah.
And I did a lot of radio, live radio and recorded radio. But the Bogota, you know, they talked to me on the phone. I was on the radio live, and they would ask me a question in Spanish, and then some translator would translate it to English. Then I would give the answer in English, translate it back into Spanish. And in 7 minutes, I had to tell this story. So eventually you get good at doing that. You know, at the end of all these interviews, man, I was on fire. I remember I remember having so much fun talking live on WGN radio in Chicago for the morning broadcast of people driving to work were listening to what I had to say. And, they told me 7 minutes, and the two interviewers dragged it out. They loved what I was talking about, so they dragged it out for 20 minutes. So it was kind of fun, but I don't really want to do this again. One interesting thing was Wits University Office of Public Relations wanted to interview me on videos, and they came to my office, interviewed me for 2 hours, and then they reduced this to a 4-minute video, which you can watch. And that video, now, I checked it a couple of days ago, over 700,000 YouTube views on this thing. And, it was a couple of 100,000 in the first 2 weeks. Amazing, right? It's nothing like Sue's elephant thing, which got... Sue's elephant video has 20 million YouTube views. Anyway, I'm not quite as famous as she is. But, when these guys came to my office to interview me, I thought they were setting up their equipment, their cameras and stuff, and so I was just killing time. And I started to sing a Taylor Swift song. And those sneaky buggers were recording me. And they put me singing Taylor Swift at the front and the back end of this 4-minute video. So maybe that's why I got a phone call from the New York Times. But I did not get a phone call from Taylor Swift, which I'm still waiting for, because I made her more famous than she already is. Maybe I should have done a Katy Perry song. Anyway, that's it. So, to think about why this was such a viral thing in the media, and part of it was that the media picked up our story and they formulated it in the way that they do, and they used the phrase "lost continent," which we specifically avoided using in anything we've written about this, because what that phrase brings to mind, of course, is Atlantis, right? And so this stupid idea of this very overrated man called Plato came up with this idea of a sunken continent, which is supposed to look like this. And so, the news, I guess, perceived that, these guys have found Atlantis, so tell us all about it. So maybe that is why it went so viral. But, it's quite silly and surprising that it went this far. It went so far that one day I was watching CNN News, and an advertising break. There was a 30-second ad break for tourism in Mauritius. So come to Mauritius, And they had some movie of a sexy-looking chick in a bikini and come to the beach and do all this thing. At the end of the thing, I took this with my cell phone, a picture of my TV screen that says, "Mauritius, home to the lost continent Mauritia." So, I tell you, I had so many requests for interviews, and I did them all. And the reason was because, it popularizes my work and my colleagues and so on, but it's also good for Wits University. Oh my God. They computed how much the value in Rand would be if they were to try to, make publicity of that nature in the New York Times and all these other places. It was millions. And so now when the dean comes to our department and says, well, you have too few students and too many professors, so your books don't balance. What about the 2 million that Ashwal? So that was a good thing. So it's really true that this article was in Cosmo with my name, and I'm delighted about that, but a little bit in bed.
In tourism in Mauritania.
Huh? They're calling it Mauritia, you see, by Jess Edwards, whoever that is. Anyway, so the story, which I'll get into now, gives an opportunity for me to explain what we really mean by the word continent. So the science reporter from the New York Times asked me, first thing he asked me was, okay, so look, when I was a little kid in school, I was taught that there are 7 continents. Are you telling me that you have found number 8? And so then I had to say, okay, wait a minute, slow down. This is not what we're talking about. And it led me to describe and explain what, as geologists, what we mean by the word continent. And the answer is different from the way geographers, I guess, and the general public. So there are the 7 continents. You can see their names. And this designation of continent, so I guess it would be an object that stands high above the ocean, and it's big, and you can draw boundaries around it if you want to, but it's completely artificial. Why, for example, is Europe considered to be a separate continent from Asia when they're connected to each other, for God's sake? So, I think there's some racism going on here, actually. The Europeans probably thinking, oh, we can't be part of Asia. No, those are Chinese and Indian people. We don't want to be associated. So we're going to be Europe and you'll be Asia. So it becomes a little silly. And then, you can look at the globe of the Earth and, there are big objects that are not considered. Why? Why is Greenland not considered a continent? Why? And there's some other big chunks of ground, Madagascar, Borneo. And so the answer is that we, as geologists, scientists, perceive the word continent in a different way than geographers do. And the definition is crustal thickness and composition of rocks and the age range of rocks and so on. And so, therefore, the word continent implies to us objects that are many different sizes and shapes. So continental crust is granitic and it has old rocks in it and so on and so on. So you find that all over the place. So I had an opportunity to explain that to the public, which I think was generally a good idea. So when I give this talk, and I haven't changed the order of the slides or anything, so it's the same slides I would give to a public talk at the astronomy club, and they know nothing about geology. So I talk about plate tectonics and explain to them how plate tectonics work and so on and so forth. I don't need to go into that with you guys. But here is the main part of the story. So oceanic crust is young, and anywhere on the Earth, it's never older than about 200 million. So about mid-Jurassic is the oldest oceanic crust that you'll see anywhere. And the reason is because it's being created now, new crust being formed and spreading apart, eventually it gets subducted. And so for us to be finding evidence of really old ages in a place like Mauritius is something that shouldn't really happen, and that's why it became so exciting to us and other people. So the idea is that continents are passive objects. They ride as passengers on oceanic crust that's forming and moving apart and eventually getting subducted. So that's plate tectonics, but on top of plate tectonics, there's another aspect of processes in the Earth that we can see, and we all know about it, and it is the formation and products of mantle plumes. So these are blowtorches, stationary blowtorches that bring hot material up from probably the core mantle boundary in many places. And they sit there and the plates move over them. So a good example is Hawaii, which is the site of the presently active hotspot or plume. And then as the plate moves along over the hotspot, it creates a chain of islands that get progressively older as you go farther and farther away from it. So the quintessential example is the Hawaiian and Emperor seamount chains. And what you can see here is this bend, which is presumably recording a change in motion of the Pacific plate at about 40 million years ago. So hotspots are an important part of the story, as you'll see, because in the Indian Ocean, where this story really takes place, there's a similar chain of hotspot volcanoes. So the active plume site is at Reunion, where there's active volcanism now. And then there's a chain of islands that goes back all the way to the Deccan eruption of enormous large igneous province at 65 million years ago, which probably killed the dinosaurs and so on and so forth. Now, this chain of hotspot islands, this track, is not as beautiful as the Hawaiian one because it's been disrupted a bit by younger spreading ridges. And so, you know, you have to consider the complexity of the processes in the Indian Ocean. But it's a similar story. So there's a hotspot volcano, and Mauritius is the second island, the second oldest island in that chain. So here is a map of Mauritius. It's a small place. So it's about 50 by 40 kilometers, 2,000 square kilometers. It's a small place. And the geology, so there's geological maps, it's stupidly simple. It's all basalt. There's almost nothing else. And people who work there have divided the basalts in Mauritius into 3 series based on their age. So the older series, intermediate, younger, different colors here on the map. Really, the big outpouring of lava is the old stuff. So that's shown in green. And this is where the big mountains in Mauritius are. So the rest of this tan-colored and the blue, is a very thin coating, almost like paint. You know, it's almost nothing. So I have the volumes here. The older, in the green, 75,000 cubic, and combined volume of the 2 younger ones, only about 35. So it's a very thin coating. And I guess, you know, looking at this map, you can almost imagine that the shape of what's left of this green stuff might resemble a caldera-shaped structure. Is probably right. And so an important thing to realize here about Mauritian geology is that the oldest rocks you get are about 9 million. There's nothing in the volcanism that's older than 9 million years ago. And then there are some younger stuff, but it's peanuts, really. So the big volcanic story is somewhere between 5 and 9 million years ago. Nothing whatsoever older. So this story, I feel obligated to share with you the background for this. And it started with this guy in 1999. A Norwegian guy called Bjorn Jamtvedt, and he and I and Trond and a student were traveling from Joburg to India, and we were doing some research project in India, but the travel agent who sold us the plane tickets, for some reason that we don't understand, organized for us to have a layover of 1 day or maybe 2 days in Mauritius. So we're going to Mauritius. So there we are in Mauritius, and we had a day or so to kill. And, you know, all of us agreed, the 4 of us agreed, that instead of spending that time doing what we're supposed to do, which is go on the beach and go swimming and snorkeling and read a book and whatever the hell you do on a holiday beach, we didn't want to do that. So Bjorn had the idea, let's rent a car and go look at the rocks. So, yeah, that's what we did. Now, he had the idea that he wanted to take a sizable sample of basalt back to Norway to see if he could crush it up and find zircons in there to get some ages. And to this day, I'm not really certain where the inspiration for that idea came from, but it turned out to be a spectacular ending. However, he did collect this sample of basalt, took it back to Norway, crushed it up. Sure enough, he found zircons in there, had them analyzed and dated, and the dates turned out to be Permian. So that would be, what, about 350 million, which is a pretty spectacular result in a volcanic island. It's not supposed to be any more than 9. So he got excited. He wrote a paper for Nature, which was pretty quickly rejected, thankfully, because those Permian zircons turned out to be contaminants from the crushing equipment that he used to pulverize the sample. If you think about it, you know anything about Norway, the geology of Norway, Oslo Rift, it's Permian. So those zircons are pieces of rocks that somebody else previously had crushed up in the same lab, and they contaminated the sample. So that was disappointing to everyone, but mostly him. But you know, Norwegians, in general, you know a lot of Norwegians, but they tend to drink a lot, and they tend to be very stubborn. And this guy would not give up. So some number of years after this, he sent two guys back to Mauritius to say, I think we should try again. And so what he did was he sent these two guys, Ebba and Hans, back to Mauritius. And this time, instead of collecting rocks, he had the idea, if we collect sand from the beach, and we have to look for the right place to do this, then we don't need to crush up the materials, and we could look for zircons without using, you know, heavy iron machinery that would introduce contamination. So what they did was they went to two sites. There's one there, and I think there's one there, and this was the tools that they used. So they bought a bunch of plastic beach toys wrapped in plastic cellophane to avoid, you know, you bring a hammer or a shovel from Norway, it could have a piece of Norwegian zircon in it. So no, we didn't want. So they brought these sand back, and they found more zircons in there. Now these zircons, so they found 20 grains, and they found Precambrian ages. So the ages 660 to 1900 something or other million years. And, you know, so they got excited again, and they published this paper in, where is I think the next picture has the reference to it. So there are two pieces of information that they used to publish this idea that there is continent under there. And I think my name is on this paper somewhere at the end. So old zircons, and then this picture is a map of the Indian Ocean based on gravity inversion modeling by a guy called Nick Kujnir, University of Liverpool, I think. And the way this works is he takes satellite gravity data and he processes it. So the data, free air, can't even read it, bathymetry, sediment thickness. And so what he's trying to do is use gravity data to make a map of crustal thickness, oceanic crustal thickness, regionally in the Indian Ocean. And he corrects for all kind of things, and he produced this map for the Indian Ocean that shows the red areas are places where the crust is abnormally thick. And you see that, so this region that comes down from the Laccadive and Maldives down to a place called Chagos, and it heads straight for Mauritius and Reunion. So he convinced us that there would be thick crust under Mauritius. And on that basis, these two pieces of information we went to press in Nature to say that there's a piece of continent under Mauritius, and furthermore, there's other pieces scattered throughout the Indian Ocean, some of which we know very well. So this object here is the Seychelles. The Seychelles we know is Precambrian granite exposed at the surface. We can collect it. And so these areas all may be underlain by continental crust. So that was our story. And here's the map and the story we came. So there's the paper, Precambrian Microcontinent, Indian Ocean, 2013, Nature Geoscience. And so what this is mainly Tron's work. So he reconstructed at a certain time in the past. Doesn't matter what that number is, but here's 750. So here's Madagascar juxtaposed against India sometime in the past. And what this work suggested was that there must have been another piece of continent in between them, which then broke apart when Gondwana began to fragment. And one of those pieces is the object we suggested was under Mauritius. So we named this microcontinent, I guess you would call it, Mauritia, I guess to glorify the island or the Republic of Mauritius, where, you know, the results and the spectacular findings were done. And so Mauritius, we suggested, was a microcontinent composed of small pieces of continental fragments under these various places that you probably never heard of, because a lot of them are submerged, but nevertheless they have possibly thick crust under them. So that was great. We got this paper published, and there was a little bit of media attention, not a great deal. Certainly not anything like I had to endure. But what became important to explain is that scientists who might read this kind of work, scientists tend to be very critical and very skeptical, and they're grouchy. And they said to us in reviews and in private and in emails and so on, how do you know that those zircons that you found in the sand, how do you know they weren't transported from somewhere else, like Madagascar? Perhaps by wind or ocean currents. I kid you not, one of the reviewers said, it is possible for a bird to eat a zircon in Madagascar
and shit it out.
in Mauritius. Other ideas, so it could be pumice floating in the sea from somewhere else. It could be that people traveling had this zircons on their shoes and they went to the tires of vehicles. These kind of criticisms and ideas are interesting, but to our mind extremely unlikely, and I'll tell you why. But impossible to counter. How are you going to say, oh, we know for sure that a birdie did not, that birdie would have had to eat the thing in Madagascar and fly 700 kilometers against the wind, remaining constipated the whole way, and then crap out the thing in Mauritius. Last time I was in Mauritius, I had some free time, and I found a little birdie, beautiful orange thing, and I spoke to this bird, and I said, did you eat a zircon and fly over here? And that birdie did not answer me, which is very suspicious. Maybe he was. So in response to this kind of criticism, the story goes a little further. And, as a geologist, petrologist, geochemist, I became interested. So I've been to Mauritius maybe about 5 times now. And a couple of the earlier times I became interested in not the basalt, because everybody's studying the basalt. There's so many papers. But there's a weird kind of rock called trachyte in Mauritius. And it is a minuscule volume compared to everything else. But I became interested in finding out how it formed. What is it doing there? So you don't know what trachyte is. Here's what it is. It's alkali-rich. That means sodium and potassium. Volcanic rock that shows alignment of feldspar crystals during flow. And so, you find these things from time to time in islands like this. And I became interested in studying the Mauritian ones. So there are 1, 2, 3, 4, 5 localities where trachyte can be found. And we went or tried to go to all of them and collect the thing. And I studied this thing to death, geochemistry, thin sections, petrology, chemical analyses, isotopes, trace elements. And I came up with a story that was published in 2016, Journal of Petrology, where I came up with a rather iconoclastic petrological view of how trachytes form. And I tell you, the volcano people, the volcanic petrologists, did not like this. So I had a very hard time with the reviews, because they want to derive this kind of rock by extreme fractional crystallization. If you don't know what that process is, it doesn't matter. But I accused these petrologists of suffering from what I call the fractional crystallization obsession syndrome. So I considered something different, but that's really irrelevant to the story. So I was studying these trachytes, and in looking at there's an outcrop of me seeing if it's magnetic using one of these magnetic pencils. Really shitty looking rocks, sort of weathered and white looking, but that's what they look like. And in the microscope, what you can see is this alignment of feldspar crystals. So really they are composed mainly of the mineral alkali feldspar, a little bit of nepheline, little bit of pyroxenes, virtually not much else. But the geochemistry of this thing, I looked at the zirconium content. And that is a lot of zirconium. 800 to 1500 ppm zirconium tells you that there's a good chance there's going to be zircon in that rock. Because zirconium is an indicator of zircon and zirconium minerals. So, in fact, I found a crystal of zircon in a thin section, so I knew it was going to be in there. So I said, why don't we take one of these trachytes and get the zircons out of there, see what their ages are. Maybe we corroborate our story and we don't have to worry about these guys criticizing us for birdies and wind. And by the way, the wind and the ocean currents they're going the wrong way. They're going from east to west. And so a zircon, which is a heavy damn mineral, is going to have a hard time being blown or transported in the wrong direction. Anyway, so I said, let's look for these. So this guy, Wiedenbeck, in Potsdam, the instrument guy, actually did the mineral separation because I was a little nervous about similar kinds of contamination from the crushing facility we have at Wits. So he agreed to crush the sample, and he didn't use any, jaw crushers or anything. What they did was they used a stainless steel rolling pin to pulverize the rock, and from there they recovered the zircons. So they did find, so in one sample they found 13 grains. And he analyzed them. And the analysis was done by this instrument, which is called a SIMS, secondary ion mass spec. It's similar to, you may be familiar with Richard Armstrong and the shrimp that he has in Australia. So this is this fantastic ion probe which allows you to put a zircon in the machine and focus an ion beam with a very tiny spot that sputters off the material and sends it through this enormous flight tube into the counters, and you can get precise ages from tiny spots on zircons, which is very cool. So here are the results. So 13 grains of zircon, 10 of them were young. And so you look at their pictures, I guess these are backscattered electron pictures of zircon grains. And these are the spots that were used to determine the ages. So 10 of them were young, and they give ages between about 5 million and 6 million with that average. So these zircons are the ones that are crystallizing from the trachyte magma, which is about what you expect because most of the basalts, as I explained earlier, forming between about 5 and 9. So we have an age of about 6. So these are unsurprising. So 10 of them, uninteresting. But three out of 10 grains gave a spectacular result. So here are the 3, 1, 2, 3 of them. And they look different. They have a lot of internal complexities that I won't bore you with. But we, again, put various spots on these zircons to determine their ages, and this is what we got. 2,500 to over 3,000 million. So these are Archean. What the hell is an Archean zircon doing in a trachyte in a volcano that's no older than 9 million? So this is the the spectacular result that led to my name appearing in Cosmopolitan. The other 2 co-authors refused to talk to the media. They said, I'm not interested in that, so Lou, you do it. Okay, whatever. What we were looking for but did not find, unfortunately, would be a zircon like this, which has an Archean center and a rim of Miocene, of 6 million years, because then you've nailed it. You're certain that this Archean zircon was picked up by a very young magma that implanted or overgrowth of young zircon. But we didn't find that. Nevertheless, this is a very interesting result. So here are the data. I won't bore you with this, but this is how you plot uranium-lead isotope data to determine ages. You have this curve called Concordia, and you plot your data on there, and where it intersects, that is the age of crystallization. So So here are the results from our 3 grains of zircon, and these red dots are the ones from the beach sand, which gave earlier ages, but still Precambrian. So that is the story that we tried to sell. Now, so here what we did is a histogram of the different ages that we obtained. The red ones are from the trachyte to 3 grains. The blue ones are the beach sand. And so you could plot a sort of a age frequency spectrum and begin comparing it to other places that might be reasonable sources for this piece of continent that we suspect is under there. And it matches pretty well the zircon age spectrum that we have in Madagascar. So we think that this chunk of continent is a fragment of Madagascar, and I'll explain why we think that in a few seconds. So our idea, so here is a plume impinging on the oceanic crust, the Indian Ocean, oceanic crust, forming a big volcano like Hawaii. And so the basalt or trachyte material, the source for that material is melting, partially melting, rising up to form the volcano and picking up pieces of this ancient continent, which we propose sits under Mauritius. So that's the basic story. So 2,500 to 3,000 ages, never been documented ever anywhere in a young volcano in the earth, and it can only mean that there's a piece of continent out there, down there. Now I've tried to draw that in blue here as a fragment. To be honest, we don't know how big it is, we don't know how thick it is, and we don't know how deep it is. It could be, a tiny little thing, or it could be a huge thing. We have no idea. So we suggest that by chance, when this plume came into the lithosphere and started to make a volcano, by chance it happened to go through a fragment of ancient continent, and that produced, it interacted with the magmas coming through it, and the zircons were picked up and delivered to us free of charge at the surface where we can collect them today. So that's our story, and there, you could think about how and why did this happen. Why would there be a fragment of ancient stuff, a small microcontinent, whatever the hell you call it? Why would that stuff be in the Indian Ocean, where by chance a plume volcano would grab pieces of it? And so, of course, we can talk about the breakup of Gondwana, and I'm not sure. I have a movie that shows some details of how Gondwana broke apart from 200 million to the present. Do you want me to show that? You may have seen it before. Yes?
Yeah.
Okay, Sue, you have to now be my technical assistant here, because I am unable to do it. Okay, so you can start the movie. So this thing is Gondwana, starting at about 200 million years ago, and it's interesting to imagine that at this time, about 200 million, dinosaurs would have been wandering about all over the place in Gondwana at that time. And so what you see here is all these fragments breaking apart. So Madagascar, India, Australia, Antarctica, Australia. At about 70 million, India decides to take off. It broke the speed limit of plate motion and crashed into Asia to produce the Himalayas. And so, this kind of little animation is mainly for an audience that would be unfamiliar with continental fragmentation, breakup processes, and so on, but it's a reality. So what we are suggesting is that in this part of the Indian Ocean, during this breakup, there's no reason why it has to be clean. There could be little pieces and bigger pieces and so on and so forth that get stranded all throughout the Indian. So we think that the Indian Ocean may be littered with small pieces of continent left behind from when Gondwana broke apart. So you can shut that off, and I'll go back to the story. Don't have much more to tell you, but I try to make this talk a bit relevant to you guys, so talk a little bit about something possibly more interesting. So, you know, in thinking about how continents break apart, one reality that we have to bear in mind is that microcontinents can form by this process called mid-ocean ridge relocation. Basically, spreading ridges can be spreading in one place, and then one day they'll decide, oops, I want to go over there. And this does happen. And so this series of pictures illustrates how that might happen. So here you have two continents and what do they call it? A ridge axe, so a newly forming ocean spreading apart. And then a plume comes in. And the plume can come in anywhere. But the idea is that the ridge somehow feels this plume and decides, hey, I don't want to spread over here anymore. I want to join this very dramatic hotspot. And so the ridges can suddenly decide to jump from one place to another. And some people say that what they're doing is following places where plumes are impinging. And so this picture, this is now ER. That's an extinct ridge. And it's now moved to here, where the spreading is now going to start to relocate. And so people like Trond, who study the breakup of continents, specifically Indian Ocean, can constrain that, in fact, in the Indian Ocean breakup, this has happened 4 times. So an example is tried to show here. So here's Madagascar and India together 83 million years ago. And then when it starts to break apart, so this is the spreading ridge, and in light gray is the African plate, this is the Indian plate. So what you see here is that at 61 million, there's the Seychelles on the Indian plate, but the ridge jumps to a different place. Suddenly, the Seychelles finds itself on the African plate. So you can transfer bits of continent from one plate to another, fragment them, leave small pieces behind. And part of our story, part of our conclusion is that continental breakup is not a simple story. It's complicated and it's messy, and it can do the things that we need it to do. So here is a present-day map of the Indian Ocean. There's Mauritius. And so all of these places that you probably never have heard of, we suggest are pieces of a former microcontinent that we've named Mauritius. We've only really documented anything that supports this idea in Mauritius, and it would be hard to sample these other places because most of them are submerged, and most of them are covered by limestone and mud and sediments, and I don't know how the hell you're going to get zircons from a place like Chagos, which is underwater, and so maybe some clever people will one day do it. So here is our new reconstruction of Mauritia. So this is at a time in the late Cretaceous, about 90 million years ago. So here's Madagascar, and here's the outline of India. And we suggest that there must have been a microcontinent that we call Mauritia in between the two. And this is kind of interesting, so a lot of the press, the media were asking me, okay, so you have this story, you got a microcontinent, big deal. Why is that important? Why? What story can I tell my readers or my listeners that might attract their interest? Why is it important? So, I had to quickly think of something that they could possibly relate to. And I said, well, let's suppose that you own a gold mine in Madagascar, on the east coast of Madagascar. And it's a really good gold mine, making a lot of money. And you have time to kill, and you are somehow slightly clued up about geology, plate tectonics, and so on. And you would be aware that at some time in the past, Madagascar and India were sitting next to each other. So you might say, let me look for another gold mine of a similar age, similar nature in India. Connect the continents back together. And that would be a pretty good idea, except that the story has to be a little more complicated now because you have to take into account that there was this Mauritian object in between the two. And so it makes it a lot more difficult to directly correlate geology from a place like Madagascar into India. You know, my good friend Martin de Wit, he's considered this, and he's written a lot of papers where he's taken the geology of Madagascar and India, try to fit them back together. It makes sense. Look, the coastlines are both straight, and so you could just take a scissors, cut out the map, put it together, and see how to correlate it. And so, you know, he's done that kind of thing, these big faults, these big suture zones. He's correlated them to certain objects in India, and he's published these ideas. But now you have to worry about Mauritius, because it ain't going to be so easy to correlate geology. So, you know, that is one of the outcomes of our work. So to use it directly as a correlation tool is going to be problematical. So we suggest, if we're correct, that under Mauritius there's a piece of continent, whatever size, whatever shape, a good question is, where did it come from? So can we correlate anything about the properties of this thing to something we know on the surface? So the three choices in the Indian Ocean would be the Seychelles, or India, or Madagascar, where in all places we have Precambrian rock that we know about. You can eliminate the Seychelles right away because there's no rock older than about 750 million in the Seychelles. There's no Archean rock. India is a good choice because there's plenty of Archean rock there, but what it lacks is the younger signature, the younger Proterozoic rocks. Not much in India, but Madagascar has everything. And so what we did was we took the geology map of Madagascar and found a region in which we could account for all of the ages that we have so far determined in an area corresponding roughly to the size of Mauritius. So that's 40 by 50 kilometers, and so it could be that an object that size of Madagascan continent exists below Mauritius. So that was our suggestion, that the zircons we see have Madagascar affinity. Next picture. So, you know, Trond is in the business of making these maps of reconstructing continents various times in the past, and he's really good at this. He has computer software that does it. And the answer is that, you know, it's complicated as hell. So he has come up with this series of time slices of what the configuration and position of continents looks like at various times in the past. I won't go through the details, but you know, what you can see here is that there are 1, 2, 3, 4 times where ridges, spreading ridges, have jumped from one place to another, and that process certainly can lead to leaving behind small fragments of continental material like the Seychelles and maybe some of these other places. I've begged Trond to make a movie of this because, you know, it's hard to really capture what the hell is going on in this complexity in 6 time slices, but making these movies is not so easy to do. So what does it say? I don't know, I'll show you this picture again. This is our new reconstruction. There's Mauritius exploration tool I've already talked about. Don't need to go into the details. I think you get the idea. So I remember 1 or 2 of the media interviewers asked me, okay, why is this important? So I explained, well, exploration tool, and they said, yeah, we get that. But, you know, what do the people living now, the normal people who live in Mauritius or anywhere else, tourists, how can they appreciate what you have discovered? And so, again, I had to think quickly and painfully about what I could answer this question with. And they said things to me like, well, okay, so you've got this piece of continent that's below the volcano there. You can't see it, you can't walk on it, you can't touch it, you can't collect it. So who cares? Well, okay, yeah, I appreciate that point of view. But I started to think about the elevation of Mauritius. Now, Mauritius has an elevation maximum 828 meters. Why? Why should Mauritius have such a high elevation? If you compare the elevation of another island, another hotspot island, so a Hawaiian island, at about the same age as Mauritius, so there's Hawaii, 9 or 10 million years ago, you're at this point. And that is what you see if you go there. So that's Necker Island, age is 10 million, maximum elevation 38. So I thought, could it be that this piece of continent we are proposing under Mauritius, which is buoyant, is actually pushing up the island and creating the elevation? If it wasn't there, maybe Mauritius would be eroded and look like this. So that is something that the people in Mauritius can relate to. If it wasn't for your piece of continent, there would be no Mauritius, right? We couldn't live there. So I thought that was pretty cool. However, this is not fair. This is cheating, and I'll show you why. Before I show you why, so here I made a plot of elevation of various places in oceans, and the black curve is Hawaii. So there is the active volcano at Mauna Kea, 4 kilometers, 4,000 meters, and then you move to older and older pieces of, in these hotspot chains, so the elevation declines by erosion and various other things, such that you form this curve, and at 30 million years ago, you're at Midway Island, which is there, and 13 meters, that's the elevation of Midway. So, you do the same thing in the Indian Ocean for the Reunion hotspot. So there's Reunion, 3 kilometers high, and I don't have very many red dots here, so it's a bit cheating. But there's Mauritius. It seems to be abnormal if you think about it this way. However, this is not fair for me to try to make this claim, because there are so many factors that affect the elevation of ocean islands, and a big one is I can't go back. So I have a list of the factors that control the elevation of ocean islands. And, the main one that I've ignored in comparing Mauritian chain to Hawaii is that the plate speed is much different. The Pacific plate is moving much faster than the Indian plate. In fact, it's about twice as fast. And so what you'd expect is that the Pacific plate is dragging these volcanoes away from the active hotspot much faster in that place than in the Indian Ocean. So, it's not fair to compare the but there are so many other factors: the age, the distance from the hotspot, the plate velocity. If there's any mid-ocean ridge around, a spreading ridge, that will affect the elevation. The age of the lithosphere is an important thing to elevation. Subsidence from the volcanic load, crustal flexure, blah, 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 erosion. So this drags in climate. The climate in the Pacific Ocean is much different from the climate in the Indian Ocean, and so that has to play a role. So it's maybe not fair for me to make a direct comparison. So I just put in some geophysics here for you, just to keep you awake, okay? Is that all right? Ray, are you falling asleep a little?
Now I'm awake.
You're awake now. Okay, so, the seismologists really don't like this story, because they look at the seismology in the Indian Ocean, and there's been a lot of new seismic deployments in the Indian Ocean, and they claim they can't see any evidence for something that would be continental under the island of Mauritius. So what they see is, I don't know, you guys know more about this than me, so you take over. How do I get rid of this damn thing? Escape. Good idea. So this is velocity versus depth for Mauritius, I think. And what they see is not a sharp moho. They see a kind of a transitional moho. And to them, they don't interpret this in terms of anything that looks continental under there. Rather, they think they're thinking in terms of what's going on here is a variable amount of what they call underplating. So you have basaltic magmas from the plume intruding probably as sills in the lithosphere and the crust, and that is what produces this variation in velocity. So here's a couple of pictures. So this is a cross-section from Reunion across Mauritius. So there's Reunion, present hotspot. There's Mauritius. And their suggestion is that the lithosphere, so the moho is the boundary between this blue and this olive green color. And so they suggest that the moho is deeper under Mauritius than under Reunion, but the lithosphere is thinner. And they attribute this to an underplating story for Mauritius. I'm not going to get into this battle with them, but you guys can take the next step here. So I'm almost at the end here. And one thing to consider is, okay, so maybe you have convinced us that there is some piece of continent under Mauritius. Is there anywhere else in the world where a similar thing may happen? And the answer is absolutely yes, because in Iceland, which is also a young hotspot volcano, we have published this paper, 20-something or other, 15 I think, to say that there's continental crust under Iceland also. And the evidence is a very similar data set. Old zircons and gravity inversion modeling that tells you something perhaps about crustal thickness. So we think that under the eastern part of Iceland, there's an extension of the Jan Mayen microcontinent that extends below the eastern part of Iceland. So there's another example. Now, there's been other documentation of old zircons in places where they shouldn't be, and one is in the mid-ocean ridges. So these two studies have documented up to Archean ages in zircons collected from either dredge samples or drill samples, I can't remember which, from the mid-Atlantic ridge. And that's interesting. I don't know how the hell you'd explain that. But you always have to begin to wonder whether they are deserving of the same criticism that we had, that those zircons are contamination from their crushing equipment. And I don't know.
No, it was a fish. It was a bird.
A bird, a fish, whatever the hell. Okay. So I'm not sure about that one. The Galapagos has recently studied by people associated with Alfred Kroner. And he has recovered zircons up to 3,000 million from the Galapagos, only published in abstract form and presented at that meeting in Cape Town, the IGC meeting. They claim that they also have a similar story under Galapagos, but they have to document carefully that it's not contamination from their crushers. So I thought about, where else should we look? And I can tell you, I do not have the energy to be doing this much more. But a good prospect might be the islands in the Cape Verde or the Canary Islands, Tenerife and Gran Canaria and so on, because they're hotspot-related volcanic islands in the ocean that are pretty close to the African continent. So at least give it a try. Maybe you find something there. Now, about a month after our paper was published in January of 2017, Nature, this thing hit the news. So there's this guy in New Zealand called Mortimer, and he suggests that there is something called a hidden continent that he named Zealandia, which exists. So New Zealand is right there, but he thinks this entire thing is a submerged continent. And he published this paper in GSA Today. And in fact, and I was called back by the New York Times guy who said, I just saw this. I want to hear your comment about it. I see their argumentation. I really have no complaint about it. But A, this is not a new idea. This guy Mortimer published a book about 20 years ago called Zealandia, which he proposed this idea. They have no zircon age. They have no age information. It's just pretty much, I don't know if it's geophysical or guesswork. But he wants this thing to be there. You can clearly tell that. I have a problem with it because this is a pretty big object. If this is the Earth's hidden continent called Zealandia, why is it submerged? So, his explanation is that when you break apart continents, you stretch the continent, you stretch the crust, which is certainly true. But I'm not sure you can stretch a continent that size to to make it, less than about 10 kilometers thick, and then have it remain submerged under the ocean. Maybe he's right, maybe not. Just call it your attention. So there are other places where people have discussed this, and whatever. So that's my summary. We found old zircons. They're not lab contaminants. They're not birdies. We think there really is a piece of Precambrian continent under Mauritius, maybe elsewhere. The age spectrum says that it is a piece of Madagascar. And what does it mean? It allows us to reconstruct continents better and understand how continents break apart better, maybe a correlation tool, maybe some story with the elevation, although I doubt it. And it supports my idea about these trachytes that the fractional crystallization obsessed petrologists hate. But how else are you going to get a zircon into a trachyte unless it comes through a piece of the crust? So therefore, the trachyte is subcrustal in its origin. And that supports the idea that it's coming from the mantle, which is what I suggested. So there's the elevation story, and then there's other places in the world where maybe you can see it. I thank you to SAGA on behalf of myself and Trond and Michael, and here we are pictured in a very fancy 5-star hotel in Mauritius doing our work and drinking some damn cocktail that they gave us. And so I thank you for inviting me and listening to my story. I hope you